Okay, so thank you everyone who are there and who will be listening to this recorded session. And today we are here for the week 5 of Unsaturated Soil Mechanics course tutorial session. And this session will be on measurement of state variables and theoretical soil water characteristic curve. So this course is actually instructed by Professor T.V. Bharat from IIT Guwahati, and I'm the PMRF scholar Satyam Tiwari, who will be instructing the tutorial session every week. So today we are going to talk about the common laboratory and field techniques for measuring soil suction. And as we know, the soil suction is a very important parameter in unsaturated soil mechanics. Okay, so while the soil suction is having two parts, the matrix suction and the osmotic suction. So for measuring the matrix suction, there are several techniques such as tensiometer, okay, axis translation technique. We also have conductivity sensor, which are based on electrical and thermal properties. We also have contact filter paper technique, okay, and then we have the total suction measurement techniques such as thermocouples. We have chilled mirror, hygrometer, resistance capacitor sensors, and humidity controls and two-pressure humidity control. Apart from that, we have non-contact filter paper methods. Okay, so if we basically divide them based on the range which are there, which range of the suction which we can measure, then we'll see that the first test is like negative column test. So this test is actually performed at very low suction pressure. That is this test. In this test, we basically have this soil column, and this soil column is connected to a reservoir, and the water level in the reservoir can be varied. Okay, so if we see that if this is the soil column and the water level in the reservoir is at this level, then corresponding to this level the soil will be saturated, right? Okay, but above this level the soil will be having the pores, right? So in this technique we change the level of the water, and we measure with the help of the soil moisture sensors. We measure the moisture content on the variation of the soil moisture content over the depth of the soil column, right? So in this test we can basically measure a soil section which is in the range of 0 to 10 kPa, because if we move further to the higher heights, like if we cannot increase the height of the column to a very great height, that's why it is having a limit that we can only measure up to like 10 kPa. Okay, so it is trying to join. Let me see. Admit. Okay, I got some. I hope you can hear me and see my slide.
Yes, sir.
Yes, sir. Okay, thank you. Can you hear me properly?
Yes, I can hear you.
Okay, thank you. Just give me 1 second. I'll change the settings for the microphone. It's fine.
Yes.
Okay, so for the week 5 of the tutorial class, I was going to start from the measurement regarding the measurement of state variable and theoretical soil water characteristic curves. So we skipped the week 3 and week 4 of the class, and those I think you'll get a additional session to cover those. And so while we divide the test, which are somebody else is trying to join, let me get here. Admit. Okay, so while we were discussing that what tests are available to measure the soil section in the soil suction in the soil. So for that, if you'll see that first one is the negative column test. In the negative column test, we usually have a soil column here, and we connect it to the reservoir, and the water level in the reservoir can be varied. So if you'll see that at the level of the reservoir, the soil below it is saturated, okay, and above it there are capillary fringes in the soil, because of which the soil get moisture. Okay, so we can measure the variation of the soil moisture at different level. Okay, according to that we can measure the soil suction in the soil, right? And these techniques, the negative column techniques, these are actually uh, these can be used to measure small suction values such as 0 to 10 kPa. Then we have tensiometer test, which can measure suction from 0 to 100, and these tests are basically very mobile, so you can use them in the laboratory as well as field. And then we have techniques like axis translation, osmotic pressure based techniques, and dew point potentiometer, vapor equilibrium. These things you might have studied in the theoretical classes. Okay, and then we have contact filter paper techniques, etc. So this is just an overview regarding the techniques which are there. The first one is a negative column technique. So here we have a column of the soil, and then it is connected to reservoir or a burette where the water level is maintained at a particular level. Then we have this soil sample, and we measure the moisture content at different height of the soil sample. Okay, in this test, as I've told, we can measure up to 15 kPa or maybe lesser than that. Okay, and the second test is tensiometer test. So this is a tensiometer which is there, and it can measure the matrix section up to a range of 0 to 100 kPa. So it basically have a ceramic cup here, and it is dipped in the soil to measure the matrix suction, and the suction which can be measured from this device, the range is very big depending on the age of the tensiometer, because as we use it on different soils, and over the time it's the cup which is there, the ceramic cup, its efficiency decreases. Okay, so there's other tests like axis translation technique. This is used to measure the matrix suction to a higher level, like 0 to 1500 kPa. Okay, these tests basically in these tests we have the control over the difference between the air pressure and the water pressure which is there, the pore water pressure, that is called a matrix suction. Okay, so in this chamber we have a soil sample which is shown here. Okay, in this chamber we can maintain a particular matrix suction level by maintaining this air pressure. Okay, so and the water pressure is also maintained at a typical atmosphere. Mostly it is maintained at typical atmospheric pressure. Okay, so within this chamber we can maintain the matrix suction, right? So we have two variables. The first one is the matrix suction, which we are maintaining by using this chamber. Okay, and the second one is we are measuring in the burette that how much water is coming out. Okay, based on that we can estimate that what is the volumetric moisture content of the soil at different times. Okay, so we have the data regarding the matrix section and the volumetric moisture content, right? So based on this we can plot the soil water characteristic curves. Okay, then other curves, other techniques are like osmotic pressure technique. Okay, in these techniques we can measure matrix suction at higher level, like 50 to 1500 kPa. Okay, so these techniques are mostly used for sandy type of, or maybe some other silty soils in which the matrix suction is not very high. So in the osmotic pressure techniques we have a solute in the solution here, and we have soil here. Okay, and this semi-permeable membrane is provided at this point, which either allows the solute to go from the solution to the soil, or it doesn't allow it, based on the test which we are the type of the test which are performed. Okay, so these techniques can measure to a higher level like 1500 kPa, but when we come to a point where we want to measure the matrix section at much higher level like in clays. Okay, at that point we go to the other techniques like dew point potentiometer techniques, which can measure from 2000 to 400,000 kPa matrix section. Okay, and then non-contact filter paper techniques, which are there, in which we have soil specimen and filter paper which is provided, which is not in contact with the soil. Okay, so this technique works with the principle that at equilibrium the chemical potential of the soil and the filter paper will be the same. Okay, and so the idea behind discussing or revising these techniques is to get to know that at different matrix suction levels, that depending on how much matrix suction we want to measure, we have different techniques which we can use, right? Different other techniques which we can use to measure this matrix structure, right? So while we come to the question, which is the first question of the assignment, we will see that a soil column is connected to a water reservoir through its base. Okay, and the water level in the reservoir is constantly maintained at a height of 10 centimeter from the base of the soil column. So if I draw it here, this is a soil column. Okay, and it is connected to a water reservoir. And it is said that the water level in the reservoir is constantly maintained at a height of 10 centimeter from the base of the soil column. So from the base of the soil column at a height of around 10 centimeter, the water level is maintained here. Fine. So this height is 10 centimeter. Then it is said that if the final height of the capillary rise in the soil column is 150 centimeter from the base, choose which of the following techniques should be used to measure the suction of the soil. So here this is a schematic diagram. So here at till this point the soil will be saturated because of the this water pressure head. Okay, after this the soil will be saturated because of the capillary fringes which will be formed. So it is said that the capillary rise in the soil column is up to 150 centimeter from the bottom. So from here it is around 150 centimeter, right? So if this point we will say we have 140 centimeter height of the capillary rise of the water in the soil sample. So if we can draw the profile of pore water pressure, then we'll see that at this point the pore water pressure will be 0, right? And below this the pore water pressure will be positive. Okay, the value of the pore water pressure, that is UW, will be dependent on the gamma W SW, right? And above this point, because of the capillary rise, there will be suction, so the pore water pressure will be on the negative side. So this we can go on to the negative side, right? So this value will be minus gamma W SW1, let's say. Okay, UW. So we want to first know that what is the maximum value of the matrix suction which is going to be there in the soil sample, based on which we'll decide that which type of technique we are going to use, right? So this height which is there, which is giving you the matrix section, that is going to be 140 centimeter. Okay, so to determine the pore water matrix section as this point, the farthest point, we are going to use UW is equal to minus gamma W and SW1. Let's say the height SW1 is this height, so that is 140 centimeter. So the gamma W1 we can use 9.81 kilonewton per meter cube multiplied by the height of the water the capillary rise. The height of the capillary rise is going to be 140 centimeter. Converting into the meter, we will write 1.4 meter. So if we'll calculate, then it will come at around 9.81 multiplied by 1.4. That's going to be minus 13.734. That's going to be meter. So it will be kilonewton per meter square. Fine. So the matrix section which we can expect the maximum metric section is going to be 13.734. so now we again go to the same chart which we have seen in the initial slides, that what technique can be used at what particular range of metric section. And what particular range of metric section. So at this point we'll see that we need to measure up to 13, and the negative column technique can measure only up to like 10, so we cannot use this technique, but we can use tensiometer as well as X-axis translation techniques, right? So these two techniques we can use, and these techniques are not useful for measuring the small metric section such as 13.7, right? So for this one we can say that we can use these two techniques, tensiometer and X-axis translation. Okay. So till now we have seen that how we can measure the metric section, and how we can use different techniques to measure the metric section. Okay, now we move on to hydraulic conductivity function. Okay, so the hydraulic conductivity function is actually the variation of the hydraulic conductivity based on the volumetric moisture content. Okay, so if you see in the saturated soils, we have studied that as the soil is fully saturated, so the hydraulic conductivity remains constant. Okay, so but in the unsaturated soil, because of the metric suction and because of the change in the moisture content at different points, the hydraulic conductivity changes over different points, right? So if we'll see in this graph, as the volumetric moisture content of the soil, if we go from left to right to left, then we'll see as the volumetric moisture content of the soil is decreasing, the hydraulic conductivity is going to be the hydraulic conductivity is going to be decreasing. Okay, and the metric section is going to be increasing. Okay, so as less and less water is available in the soil, it goes to the unsaturated state. At that point the metric section will increase, because of which it will hinder the path of the water to flow, so the hydraulic conductivity will decrease. So as theta will the moisture content will decrease, the hydraulic conductivity K will also decrease, but the suction will increase, right? And this is also shown in this plot, because as the metric suction is increasing, the hydraulic conductivity is decreasing, right? So the metric suction is increasing, the hydraulic conductivity is decreasing. Right. So to measure the hydraulic conductivity function, we in the saturated soil we basically use the falling head techniques. We also use constant head techniques depending on the soil. That falling head techniques we basically use for fine grained soil, constant head we use for coarse grained soil. Okay. But in the unsaturated soils we have few techniques to measure the hydraulic conductivity. One of them is multi-step outflow method. Okay, so if we'll see the multi-step outflow method, it is basically the same as the method which we have seen here, that is called X-axis translation technique. So let me show you X-axis translation techniques, in which we have a chamber where we have the freedom to regulate the metric suction value by regulating the pore air pressure, okay, or the air pressure, and based on this we can say that we have the regulation over the metric suction. Fine. So this multi-step outflow method is actually the same as that method. So in which we have like if you'll see the flow equation which is there, that is del upon del z, and the k is the hydraulic conductivity, and del h upon del z is equal to del theta upon del t, which we know. Okay, so in this equation if you'll see in the multi-step outflow method, what happens is that we have a high permeable disk here, okay, and high air entry which is available here, and here we have the arrangement to measure the pore water pressure, okay, and the pore air pressure which we can maintain in this chamber. Okay, so basically we have control over UA minus UW, that is metric suction. Fine. And in the soil, which you'll see as you'll apply the more air, pore air pressure, the water will permeate and it will go from this high air entry disk to this reservoir. Okay, then we can measure that how much water is coming out, right? We can measure the volume, how much water is coming out at a particular time, Vt. Okay, so this equation, if we will further simplify, that will result into d5 by dz2 and d5 by dt, del 5 by dt, del t. The d term which is there, that is called hydraulic diffusivity. Okay, and we have seen in theoretical classes that this hydraulic diffusivity is calculated in the experiment in the multi-step outflow method to determine the hydraulic conductivity, that is K. Okay, these two are related. Then this equation which we see here, the flow equation in terms of hydraulic diffusivity, if we apply the boundary value conditions, okay, then based on the boundary value solution, the Gardner gave a boundary value condition. The Gardner gave a solution that says the ln V infinity, the V infinity is the water which will be collected here at time infinity, okay, after at equilibrium, we can say after a long time. Okay, and the Vt is the volume of the water which have come out at a particular time t, right? So Vt is the variable which depends on the time t, right? And then the V infinity, if we take the log of this, then it will be equal to log of the ln of log at the base e of 8 upon pi square minus capital D pi square t upon 4h square. So if you will see this equation, this actually is y is equal to mx plus c type of equation or linear equation, right? So the intercept which is there, that's going to be ln 8 upon pi square, and the slope of this line is going to be x-axis is t, y-axis is vt, and y-axis is v infinity minus vt upon v infinity. Then the slope of this axis is going to be d pi square upon 4h square, right? So in this way, if we proceed further, then we'll see that multi-step outflow method is used to determine the hydraulic conductivity or the hydraulic conductivity function. Okay, and but it has some limitations, that we cannot work on higher suction values in this experiment. Okay, so it may not be applicable for clays. It is useful for sandy soils and some silts, mainly dependent on the how much water can be permeate, or how is the high air entry disk there. Okay, and there is also a limitation that we need to apply small suction increments, which we'll see later at the end of this lecture. Then will be suction values to analyze the result. Okay, but if you apply the small suction values, then the water which will be coming out here will be very less. Okay, so that is one of the problem in this experiment. Okay, so we have talked about the hydraulic conductivity function, and now we are going to talk about the soil water characteristic curves. Okay, so the soil water characteristic curves are basically the relationship between the phi, that is volumetric water content, and the psi, which is the soil suction. Okay, and or it can be the relationship between the gravimetric water content W and the psi. Okay, and apart it can be the relation between the SR, that is the saturation at the retention level. Okay, and so the soil water characteristic curve is basically a curve which signifies that how the drying and the wetting process is happening in the soil, right? So if you'll see in this curve, okay, and if we see in this curve, if we start from the saturated condition in the soil and we start drying the soil sample, then it will follow this path. Okay, and at a particular point it will start following this part, and after a particular point we'll see that this theta r, after that it will not be able to extract any water from the soil, right? And If we repeat the wetting cycle, then it will follow another part to reach at this point, right? So we are discussing that two types of curves are there. Okay, first one, hydraulic conductivity function, how we are calculating, and how we are calculating the soil water characteristic curves. Okay, so this soil water characteristic curve is actually made based on the experimental results, but we need to have some prediction models based on which we can we can calculate the these soil water characteristic curves, right? So one of the model is of Brooks and Corey. Okay, this Brooks and Corey model uh, dictates a non-continuous function for hydraulic conductivity. Okay, and for soil water characteristic curve, sorry. So this function says that the volumetric moisture content theta at particular time is equal to phi s when the suction value is less than the air entry pressure or the bubbling pressure, psi b, right? And this theta will be equal to theta r plus theta s, the volumetric moisture content at saturation. Okay, and the minus the theta r, the residual volumetric moisture content, water content, right, multiplied by psi b upon psi is a metric suction at a particular point, and to the power lambda. Lambda is the pore size distribution factor, right? So let me just erase this thing. Okay, so if we'll see in this model, we have a function by which if we know the value if we know the values of the suction from the test, then we can calculate the values of the theta or the pore water pressure, the volumetric water content of this in the soil, right? So based on this, we can plot the soil water characteristic curves. If we plot suction here, we plot theta here. So based on this, we can plot this curve, right? So this is the model which can help us in plotting the soil water characteristic curve. So, okay, so in this expression, if we'll see, if we rearrange this expression, then we'll see theta is equal to theta r plus theta s minus theta r and psi b upon psi to the power lambda. If we rearrange it, that's going to be theta minus theta r divided by theta s minus this theta r will be equal to the psi b upon psi to the power lambda, right? So this expression is written here, and this is the capital theta or the big theta is the normalized water content. Okay, because it is theta minus theta r upon theta s minus theta r. Okay, so so the normalized water content is directly related to the suction value in the soil. No, okay, so to use this model, this Brooks and Corey model, we'll see we can either vary the value of the air entry pressure, that is psi b. Okay, then as the air entry pressure will increase, we'll see that at a particular degree of saturation, the metric suction value will increase, right? And also we can vary the value of the lambda. Okay, that is a pole side distribution factor. If we vary the value of the lambda, then we'll see at a particular degree of saturation, as the value of the lambda increases, the metric suction decreases. Okay, so to understand how these model work, how we can use this model to predict the soil water characteristic curve, we'll see an example and solve it. Okay, if you people are having your here it is, if you people are having your laptops with you, then you can try along with me, because I'm going to solve it on an Excel program. Okay, because that's going to be easy. So the question here is that the temperature test hole conducted to determine the SWCC of sandy soil. Okay, and the results are shown in this table 12.1, and we need to model the SWCC. soil water characteristic curve using the Brooks and Core equation. So if you'll see the Brooks and Core equation, okay, then we'll see that this equation is the Brooks and Core equation, right? So here in the question we have been given two things. First one is UA minus UW, that is nothing but psi, okay, matrix suction, and we are giving the degree of saturation at different time, different suction values, right? So this equation, which is written in terms of theta or the volumetric moisture content, can also be used in terms of degree of saturation, because those two are linearly correlated, right? So if we come here that these values are of suction are provided and these values of degree of saturation are provided. If we plot these values on an XY plot, x-axis will be degree of saturation, y value will be matrix suction, then these points you can plot easily, right? These point which you see here, these can be plotted based on x and y value, right? So let's move to let me share my screen again, and I'll share Excel sheet where I'll be calculating these things, okay? Okay, so here I have solved this one, but I'll be solving it again just to show you. Okay, so we'll start from here that in the question it was given that we have the matrix suction values of 0.1, 1.18, 1.86 and etc, and the degree of saturation 1.99, 0.95 etc. Okay, so let's jump to the Excel sheet and okay, so let's jump to our Excel sheet and we'll see I've noted down these values here which are given in the question. So the value, this value is observed suction value, that is nothing but UA minus UW, okay, and this value is the observed value of degree of saturation, right? So as we know that the BC model, Brooks and Coley model, says that this capital theta will be equal to theta minus theta r, when theta s minus theta r is equal to psi b upon psi to the power lambda, right? So here if we convert this equation in terms of suction, then we will see that if we take a log on the both side, okay, then we rearrange the expression, then we'll find out the suction value is equal to the 10 to the power log of psi b minus 1 upon lambda log of this. You can easily find by rearranging this equation, okay? So here if we observed carefully, then we'll see there are some unknowns which we need to have, or the parameters which we need to have before applying this equation to obtain the suction value from the model, right? So the first parameter which is there, that is the value of the lambda, okay, force side distribution factor. So this one is there. So for the initial point we will just put some random values for lambda, okay, and the bubbling pressure which is there, that is also unknown, okay, here, and these parameters are tuned based on the experimental results, okay. The experimental results are there, so our objective is to find out the optimal values of these three parameters, right? Then only we will be able to apply this equation, and this will give us the prediction model for the soil water characteristic curve, right? So so here the bubbling pressure value I'll be putting, let's say 1.5, okay, the SR value, okay, the SR value which we can obtain from this plot. Also this plot is nothing but I plotted these values which are obtained from the experiment. So if the SR value, you will note here from here the degree of saturation when the matrix suction is the highest, then it will be around 0.3. Right. So here I have written the three parameters which are there. The degree of saturation SS value I have written 1. Okay. And here you'll be wondering that these values are given in theta, but I'm using in terms of S. Okay, so as I've told that theta and S are linearly correlated, so you can use this equation by putting the value of S also. Fine. So if we apply this prediction model, then we can predict the value of this suction parameter. Okay, this suction by applying this equation. Okay, so we'll apply this equation here. Okay, so that's going to be 10 to the power log of the value of the bubbling pressure psi b is going to be here. Okay, then we'll log this value minus, then we have 1 upon lambda, so that's going to be 1 upon the value of the lambda is provided here, so we'll write f4, we'll log this value too, and then we have in multiplication the log. Okay, so the log, we are using the log at the 10 here also. I think I have missed, that's going to be log at the base 10, right? Multiplication is missing here. Okay, so log at the base 10, then we have this value theta minus theta r, or we can use S minus SR upon SS minus SR. Fine. So the value of S is provided in this B column, right? So we can write B2. Let's put a bracket. We can write B2 minus the value of theta r or SR, we can say, is written here. So we can use this SR, then we'll put a bracket, then we'll write the denominator part, that's going to be theta S minus theta r or SS minus SR. So let's put SS, log this value, put a bracket here. Okay, and the value of the SR also. Okay, fine. Okay, so here we see the prediction, the predicted value of the suction for this particular observation is here using this BC model. Okay, now we'll copy this formula for all the values. Okay, then we'll see these prediction values are obtained, right? But these values are based on the parameters which we have the values for which we have assumed here, right? So we need to tune these values to obtain the optimal to obtain the best fitting model. Okay, so here if I can, okay, fine. So here if you'll see in the plot, I plotted two values. The first one is the observed values of the S, okay, and the second one is the predicted values of the suction, right? So these values which you see is the X. Somebody is trying to join. Let me. Okay, so here you'll see that these dots, these points are indicating the values of these observed values from the experiment. Okay, so x-axis is degree of saturation, y-axis is matrix suction. Okay, then you'll again plot the values which you have obtained from the prediction model of this Brooks and Coley. Then you'll see these values are we have obtained as these predicted suction, and observed as is the same, right? So this model, if you'll see now, it is fitting okay, but this is not the optimum model which we want, because we want to fit it to an optimum point. Okay, so how we can do it, that in Excel you have a function where you can use this solver. Okay, if this is not activated in your Excel sheet, then you can go to your files, then you can go to your options. Okay, then there will be add-ins, right? So here you can manage your add-ins, go there and just activate this solver add-in, right? So in this way you will have this solver add in here. What this solver does is that if you will if you will define to this solver that you need to optimize this value by varying these particular values or these values, then it will vary these values to find the optimum optimum solution for that particular value. Okay, so here what we need to do, we need to first find the error which is there between the predicted and observed value. The predicted values are here and the observed values of section are here. So let's take a square for positive value. So these are the error which are there. So if we sum of these error, the sum of the error, that's going to be this. So what we want is that the sum of these errors should be minimum to have a best fit model, right? So we'll just go to solver. Okay, then we'll set the objective that we want to minimize this sum of error, right? What we want to do, we want to minimize the sum of error. Okay, how we want to minimize that? By changing the variable cells. What variable cell we want to change? These three values we want to change. We don't want to change SS, that's going to be 1 only. Okay, we want to change the value of lambda, we want to change the bubble pressure, we want to change the SR value, right? So by doing this, if we click on solve, then it will calculate this optimum model which is the best fit. Okay, and it has also calculated the values of lambda as 0.74, the bubbling pressure 1.2, SR 0.26, like that. Okay, so if we click OK, then we'll find that we have obtained the optimum values of lambda, the bubbling pressure and the SR, right? So here we with the help of this solver, we have easily solved this to determine the values of these state parameter lambda, psi b and SR. Okay, so at the end the summary is that we had the observed values from the experiment. Okay, we used the Brook and Coley model to predict these values of the suction. Okay, and then we minimize the error in the prediction by tuning the values of lambda, the bubbling pressure psi b and the SR. Okay, so in this way we have obtained the optimum values of lambda, the bubbling pressure psi b and the SR, these three values. Okay, so let's go back to our slide, then we'll see. We have obtained the optimum value of lambda, psi b and SR. So the values written here are based on the book from where I've taken this example. Okay, that is the Ning Blues book. Okay, but the values we have obtained are slightly different from that, so that's fine. Okay, and so, we can also see here that this model is fitting very well to the experimental data. So we can say that the Brooks and Coley model is very good and it fits very well to the experimental data. Okay, fine. Similarly, this is the first model, the Brooks and Coley model. Okay. Battery is down. Just give me 1 minute so that I can get my charger. Okay, so sorry for that. Where we were. So we were here in Brook and Corey model. Okay, based on this model, we have used the experimental data, and then we have also modeled the behavior or the soil water characteristic curve using the Brooks and Corey relationship, which is given here, right? So now what we want to do is that we'll move on to the next model, that is Van Gunchen model, that is VG model, given in 1980. Based on this model, they provided that the value of this normalized volumetric water content capital theta is going to be 1 upon 1 plus a psi to the power n and to the whole power m. So here you'll see there are three fitting parameters. Like in the last problem which we have seen in Brook and Coley model, we had the fitting parameters as only lambda, right, or not the, and the three parameter which we are obtaining from the optimization techniques. Okay, then in the VG model and the Van Gunchen model, we have three fitting parameters, that is a, n and m, right? So we need to obtain these parameters, and also we need to obtain some other parameters such as theta r. Okay, and okay, that's also, there are four parameters which we need to obtain to obtain the optimal values of these parameters to obtain the best fit model, right? So here the value of m can be 2, m is equal to 1 upon 1 minus 1 upon n, and 1 minus 1 upon 2n also. Okay, so in the Van Gunchen model, it has the flexibility that it can be applied to a wider range of suction. Okay, and it's also there that it is a continuous model, so you'll only see one equation, right? And in the Brook and Corey model, you had these two functions, so it is not continuous one. Fine. Let's let's move on to this point, that if you'll see this expression of capital theta. Okay, if we if we do the derivation of this expression in reference to the suction value del capital theta upon del psi, then we'll see it will come to minus m. Okay, minus m will come here, 1 plus 1 upon to the power n, and to the power minus 1 upon minus m plus 1, and then we'll derive this. Okay, then if we'll simplify this, then we will reach out to expression that will be equal to del theta upon del psi is equal to minus a into m into n multiplied by 1 plus a psi to the power n to the power minus m plus 1 multiply a psi to the power n minus 1. Okay, so in this expression, if you'll see, if the psi tends to 0, okay, in that case what will happen, the value of the okay, fine, when the psi tends to 0 or the matrix suction is not there, okay, at that time, if the value of n is 1, who else is trying to join? Okay, so if we take the value of n as 1, then we'll obtain that if we put n is equal to 1 here, then this value will be equal to 1 and minus 1 0. Okay, and del psi by del theta upon del psi will tends towards infinity. Okay, and if we see here that this when del psi by del theta upon del psi will tends toward infinity, the value of diffusivity, which is equal to k del psi upon del theta, it will be equal to 0. Okay, so in that case, we'll see that this expression which is there Van Gunchen model is not defined. Okay, so there was a question that in Van Gunchen model, when the value of the parameter n is 1, okay, so what will happen? So at that point, what happens is the diffusivity tends to 0. Okay, when the suction approaches to 0, when the psi value approaches to 0, the diffusivity also tends to 0. Okay, so the diffusivity becomes 0 when the suction approaches 0, right? Okay, so similar to the BC model, okay, and Brook and Coley model, we will do a similar exercise for Venn Gunjan model. Okay, so this example which is given, that the previous example which we solved, problem 12.1, we need to solve this using Venn Gunjan model. Okay, so here you can solve it either with and without the values of m is equal to 1 upon 1 minus n constant, 1 upon 1 by n constant, or not. So we'll just solve it for one case, okay, there where the m will be equal to 1 minus 1 upon n. Fine. So the values which are given here are the same as given for the previous problem. So we'll again switch to the Excel sheet. Okay, so we'll again switch to the Excel sheet, and we will just make a duplicate of this one. Okay, so here I've written the equation for the VC model. Okay, Venn Gunjan model that gives the capital theta is equal to, it is theta minus theta r upon theta s minus theta r on 1 upon 1 plus a psi to the power n to the whole power m. Okay, so here are the observation from the laboratory, that is observed suction, and then we have observed value of saturation here, and we need to fit the Venn Gunjan model in this data, right? So first we have plotted this data in a soil water characteristic curve, that is granulometric suction and degree of saturation, or you can switch the axis also. Then we'll apply the prediction equation given by Venn Gunjan, and then we'll plot this data also in the same plot to see how well it is fitting. Okay, then we'll vary the values of a and m and sr to better fit this model, right? So in the last expression, if you'll see, I have predicted value of the suction. Okay, and in this expression I'm going to predict the value of the soil, the degree of saturation, right? So this is one thing to note, that these expressions are reversible. Okay, either you can obtain the value of suction based on the value of theta, or the volumetric moisture content, or the degree of saturation, and or reverse, you can obtain the value of degree of saturation or the volumetric moisture content based on the values of suction, right? So that's why I have done one problem for prediction of the suction and another for the prediction of S value. So to predict the value of S, or the degree of saturation, we can use this expression, and in the place of the volumetric moisture content we can use the degree of saturation also, as they are linearly correlated. So here we need to find the value of S, or the theta. So that will be equal to, if we send this part denominator this side, so this will be theta is equal to theta r plus, in the bracket, theta s minus theta r multiplied by this term, right? So we'll apply this equation here. So let's write the formula. That's going to be theta r, the value of theta r or sr is here. Okay, let's first fill some values here. Let's say a is 0.5, n is 0.3, the value of m is equal to n, the value of m is going to be, okay, let's see, that is 1 minus what is given in the question, that's going to be 1 minus 1 upon n, right? So we can use m is equal to 1 minus 1 upon value of n. And the SR, don't mind the values here because we are anyways going to optimize it. Okay, the values of the SR, let's say 0.3 here also. Okay, now we'll write the expression, let's increase this one to 1 or 0.8. So okay, right. So now we'll type the equation here. That's going to be the predicted values of S is equal to theta r or SR. Let's log this one, and plus theta s minus theta r. The theta s is corresponding to SS, Let's log ss minus sr. Let's log this one also. Okay, and multiply it by this whole expression that is there, 1 upon 1 plus a psi to the power n to the power m. Okay, then we'll write 1 upon, that's going to be 1 plus, in the denominator 1 plus a psi to the power n. The value of the a is here. Let's log this value. The value of the psi is going to be observed suction value, that's going to be here, and we'll not log because we want to vary this value over this table, right? And then we'll close the bracket. Let's do power. Okay, then we'll close this one, and the whole power is to the power m. Okay, the value of m is here, and log this one also. Fine. So this is the predicted value of saturation which we have obtained, right? So here if you'll see, as I plot this, these values are coming here. So now if I do the same exercise as I've done earlier to obtain the predicted versus the obtained value, so here if we reverse the repeat the same exercise to predicted values minus observed value, the predicted value is here minus the observed value of saturation is here, and that's going to be to the power 2. And if we provide the, if we obtain the sum of these errors, then it's going to be this one. So again what I want to do is I want to minimize this error by varying these values. Okay, so again I'll go to the solver and I'll select minimize this error value, the sum of the errors, by varying the values of these parameters, right? I'll click to solve and it has solved. So here you'll see you have obtained a very good fit of the model, right? Using this Venn-Genshin function, Venn-Genshin prediction model. Okay, so at this point you can see for the BC model we have obtained a very good fit, and also for the Venn-Genshin model we have obtained a very good fit here, right? So so in this way we can, by using the spreadsheet, we can easily solve these functions. Okay, easily use these prediction models to obtain the better fit, right? Okay, so using these spreadsheet we can obtain these parameters. Okay, we can let's take a 5 to 10 minutes break, then we'll continue the session from here. In between, if you people have any doubt, please do ask. Okay, so let's start with the, as we have discussed two models. The first one was the Brook and Corey model for soil water characteristic curve prediction modeling. Then we discussed about the Van Gunchen model, that's in 1980 for the soil water characteristic curve. And we have solved two problems with the help of a spreadsheet to better fit the model to the experimental data. Now there are other models also, such as Fredlin and Zing model given in 1994. Okay, so the basic difference between the Van Gunchen and Brook and Corey model with the Fredlin and Zing model, if you'll see here that in this model, the volumetric moisture content is related to the value. This is exponential value, the e to the power 1, and the value of the suction. But this formula is not reversible, so you cannot write phi in terms of theta or the volumetric moisture content, but you can write theta in terms of phi, right? But in other two models, you can, these are reversible, so you can write both in terms of other. Okay, so this is one of the example which you can solve similarly as we have solved the two models which we have seen earlier, right? So in this example, if you'll see, the data is given regarding the suction in relation to the volumetric moisture content, and these data are used for two type, glacial till and silty loam. Okay, then it is asked that for glacial till and silty loam, soil water characteristic data is provided, and we need to model and compare the WCC for each soil using the Briggs and Corey and Van Gunchen model and Fredlin and Zing equation. Okay, so we can again use the spreadsheet and model these model the Van Gunchen, Brook and Corey model along with Fredlin and Zing equation, right? So this I leave for you to do on your own. And apart from the three famous models we have discussed, there are other models such as Campbell model of 1974, Gardner model of 1958, and Bruscart model and McCree and Buck model. Okay, these expressions, this is theta. These expressions are also, they relate the volumetric moisture content with the suction value. Okay. Here also the this W is the water content at any soil suction. Okay, and this is not the volumetric water content, this is the gravimetric water content. Okay, and here also these two are in gravimetric water content. So we have previously discussed about the hydraulic conductivity function. Okay, how to calculate the hydraulic conductivity function in laboratory. Okay, now we are going to discuss about the models of hydraulic conductivity function. Some simple empirical models and the statistical models are provided to model the hydraulic conductivity function statistically as well as empirically, similar to the case of soil water characteristic curve. So here the first model is the Richards model. Richards model is like a simple line equation, y is equal to mx plus c. Okay, so here the hydraulic conductivity k is related to the suction value, and there are two parameters a and b which we need to determine based on the experimentation. So it is an empirical relation. Similarly, the Gardner have provided another equation, another model which relates hydraulic conductivity with soil suction, that is equal to K, the hydraulic conductivity at saturation, that is constant, and A into psi. So here 2 value to the power n. Here two values are there. Okay, these are A and n which we need to determine based on the experimentation. Okay, so this is also an empirical relation, and and as we have seen in here, like in the Van Gunchen model, there were three fitting parameters. Similar to that, here, similar to this, for the hydraulic conductivity function, we also have these fitting parameters. right? So these fitting parameters we determine based on the best fit, as we have seen earlier also. So Brooks and Corey also provided the hydraulic conductivity function model, and it is also a non-continuous model where K is equal to Ks for less than the air entry pressure value, and for more than air entry pressure that's going to be Ks phi psi b upon psi to the power n. Okay, and in the Campbell model in 1973, it says that hydraulic conductivity is equal to saturated hydraulic conductivity multiplied the volumetric moisture content divided by the saturated moisture content, volumetric moisture content to the power n. N is the fitting parameter here, and these are the empirical correlations, but there are some statistical correlations also. These correlations are based on the distribution of pore spaces, okay, distribution of these voids in the soil matrix. Okay, this section is drawn, and based on this they have calculated these formula statistically. The first formula is of Jackson's. Okay, so the Jackson formula relates the hydraulic conductivity with the value of this high volumetric moisture content at particular particular point of time I, and this at saturation, and this value which you see here, J and I, these are the iteration constant, and Hj is the hydraulic head. Okay, and this will see that how we use these equations to solve. Okay, then there are models of Bunden and Mollem. These are also a statistical model derived based on different principle, like Jackson's formula is derived based on Hagen-Pasley principle. Okay, so so based on this Jackson model, we can do one numerical. Okay. So the numerical states that the soil water characteristic curve of a sandy soil is shown in figure 12.15, and this is figure 12.15. The soil water characteristic curve is shown here. Okay, these points you can see, and between suction head, that is H. Okay, or you can draw it phi here also, and the volumetric moisture content theta. The saturated hydraulic conductivity Ks is given as 1.8 into 10 to the power minus 3 centimeter per second. Then we need to use the Jackson formalism to predict the unsaturated hydraulic conductivity function from SWCC. Okay, so the Jackson formula as given here. Okay, it in this formula what we need to do is we need to take small increments. Okay, and in these increments we need to calculate the suction heads. Okay, based on these suction head we can calculate the hydraulic conductivity, right? So we'll see in a while that how we'll do it. Okay, so so to start with, what we'll do, that will start from the volumetric moisture content, that is going to be for the saturation. Okay, then we'll take small increments. Okay, one increment will be equal to, let's say this one is 0.3, 0.32, 0.34 and 0.36. so first increment or the decrement is from 0.36 to 0.34, like that. Okay, so one step will go, and we'll take 15 iterations to reach here. All right, so let's see how we do it. So we see here that the degree of the moisture content at the saturation, we can read it from here, is going to be 0.36, around 0.36. Okay, and this for the first increment we have taken theta from 0.34. Okay, and similarly we will consider it for different intervals. Okay, so let's see the formula. We have written for the first increment, the theta 1 is going to be, or the for I is equal to 1, theta 1 is going to be theta saturated, that is 0.36. so we are starting from here and moving in this side. Okay, so the theta 1 is going to be theta saturation for I is equal to 1, so that's going to be 0.36, And as when we'll apply this formula, then in this formula if we put the value of I as 1, okay, then we'll see this 2 into 1 is equal to, and the j will vary from I to m. Okay, the value of m is equal to the number of increments which we are taking. So we are taking 15 increments. Okay, so for we are taking this for the 15 times. Okay, and then we'll see that for the I is equal to 1, this is going to be 21 into 2. For I is equal to 1, if we'll solve the numerator, this one part, and the denominator, the summation part, then these two will be the same. Okay, so these two will cancel out. Then the value of the k will be equal to ks theta I upon theta s to the power c, and we know that theta I is equal to theta s for this case, for I is equal to 1, from 0.36 to 0.34. Okay, so this one will be 1. So for first condition, k theta 1 is going to be ks only. Okay, now we'll calculate for I is equal to 2. Okay, so for I is equal to 2, we start from 0.34, we move to 0.32. Okay, and so we'll write here k is equal to, let's erase the above part, right? So for I is equal to 2, we'll write theta 2 is equal to 0.34. So we are starting from 0.34 and moving to 0.32. Okay, so the value of ks is going to be 1.8, this value 1.8 into 10 to the power minus 3 multiplied by the theta I value is going to be 0.34, the starting of the second iteration, and the value of the theta s is going to be 0.36, the value of volumetric moisture content at saturation, right? And moving on to the part of numerator and denominator. So here if you'll observe that if we put the value of j as 1, okay, then it will be 2 into 1 is equal to 1, right? And plus 1, so that's going to be 3 minus the value of I is 2, 4, so that's going to be minus 1. So we'll neglect the value which are in minus. So for j is equal to 1, we are neglecting the term. Okay, then we go for j is equal to 2. So for j is equal to 2, if you'll see here, if you put j is equal to 2, 2 to the 4 plus 1, that's going to be 5, minus I is anyways 2 for this second iteration, so that's going to be 4, so it will be 1. So we'll write 1 divided by h square. So what is h? H is the mean value of the suction head at this particular increment. So if you'll see in this increment, 0.34 to 0.32, then this is the mean value. And if you observe this value, then it's going to be somewhere, if you observe this value, then it's going to be somewhere around 2.7 or 2.6 something. So we'll write 2.75 and to the power minus 2 or h square, right? H square. Okay, let's move to for j is equal to 3. For j is equal to 3, what will happen? This 2j plus 1 minus 2i, that will be equal to 3 to the 6 plus 1 minus 4. That's going to be 3. Okay, so if you'll see the denominator part, that is 2j minus 1, that is anyways going to be same, summation of 2j minus 1 upon h square. Okay, so because there is no I part here, so for all the iterations, this part will be same. So we can calculate this as, for j is equal to 1, it is 2 minus 1, 1 upon 2.4 square, the 4 square, the first one 2.4, for the second one 2.75, third one 2.96, then 3, Then at the end for 15 iteration, it's going to be 30 minus 1, 29, divided by the value of the 15th iteration is going to be around, this one is going to be 80, or you can write 82 as per the book. Okay, so this is going to be 82. So in this way the denominator is always equal, and we have calculated is a 9.387. okay, and if we perform this operation in a spreadsheet, then maybe it's going to be easier. Okay, then we do it for j is equal to 3. Okay, so this term will be obtained for j is equal to 3. We have obtained 3, and this term will be obtained for j is equal to 4. If you'll see, then it will be 8 plus 1 minus 4, then going to be 5. So this, and this way we can go up to the j is equal to 15. So 27 upon 82 to the whole square. Okay, so let's erase this thing, and so what did we observe from here is that we need to perform this operation, or this operation we need to repeat for k for the values of j from 1 to the m value, or number of iterations which we are taking. Okay, so we are taking 15, so for the 15 number of intervals which we are taking, right? So in this way we will calculate k theta 2, that will be this thing, k theta 2. Similarly we will do this for k theta 3. Okay, for the third iteration we will do it, and we need to repeat this operation till k theta 15, right? So after repeating this operation for every value of every increment of theta, then we'll see that we have obtained a plot that we have calculated the value of k, that is a function of theta, for every value of volumetric water content theta, as well as for different values of soil suction h, right? So we can plot two plots, that is hydraulic conductivity k versus volumetric water content theta, and hydraulic conductivity k versus h, hydraulic conductivity k versus matrix suction h. Okay, so this plot will be, the hydraulic conductivity will increase as the volumetric water content will increase. So we'll see, as the volumetric water content will increase to the saturation level, okay, then the hydraulic conductivity will be maximum. Okay, and similar for the suction, as the water content will increase, the suction will decrease, right? So in that case we'll see at the suction if we see as the suction decreases, the hydraulic conductivity increases, or the opposite, as the suction increases, the hydraulic conductivity decreases, right? So in this way we can use this formula of Jackson. Okay, fine. So there's a question that choose that which statistical method can be used to determine hydraulic conductivity function. Okay, so for hydraulic conductivity function, what are the statistical models which we can see here? So these are Jackson model, Burden model, Mollem model. Okay, let's go back and see the question. So from here we can say the Burden and Mollem model are the statistical model, and Richards and Cambrian model are the empirical model. Okay, so we have solved this question using the the statistical model. Okay, now we can solve the hydraulic conductivity function using the model which are there, it's empirical models. Okay, so see this example, that there is the data is given of soil suction head versus relative hydraulic conductivity, and we need to fit a model into it. And which models we can fit? The Brooks and Corey model, the Gardner model. Okay, one parameter, two parameter model. So we'll only, for now we'll only set the one model. Okay, it's a one parameter model, and the Richards model. Fine. So these are the three models. Okay, and Gardner we are using the two parameter model. So these are the three model which will be fitting. Okay, the data is provided in this table, and we'll be using these expressions and obtaining the value of these fitting parameters by using the Excel sheet. Okay, so again let's move to the Excel sheet. So we are trying to do the HCF model. Okay, so maybe we'll do the HCF model for using one method. Okay, so here you see I have noted down the suction head and the observed value of hydraulic conductivity. These are provided from the experimentation. Now to predict it, let's say if you are using the Gardner equation. Okay, so where is the Gardner equation? This Gardner equation you will see here. This one is the Gardner equation that provides the hydraulic conductivity is equal to the saturated hydraulic conductivity upon 1 plus a to the power psi to the power n. Okay, so these two parameters which we need to determine, right? So here I have written the value of a. I have written something like 6, or you can write 7, or value of n, let's say I have written 3. Okay, so as I'm writing the value, I'm also plotting it alongside. So you'll see these points, the blue points which you see, these are the observed values of hydraulic conductivity, and these points which are there, the gray one, these are the predicted values using Gardner. How I've obtained this? Just come here. Okay, the value, and let's see, we'll do it again for the Gardner value. The Gardner empirical equations, the Gardner equations to formulate the pair, to do the pair prediction model, we'll write that is equal to the K predicted will be equal to K upon, that is K saturation. Let's say the K saturation is 1. Okay, and divided by, and we need to log this value, and that is divided by 1 plus a psi to the power n, right? This one, a psi to the power n, right? So let's move here and we will write the value of a as provided here. We'll log this, multiply value of psi. The value of psi suction head is given here. Okay, then we'll click here and to the power n, and we need to log. Fine, so these are the value which we have obtained. Okay, and there are some discrepancies, I think. Let's see. Okay, so if we copy this one here, then we'll see this model is not at all coming very perfect. So what we need to do, first we'll obtain the predicted minus observed values. The square predicted minus observed value, then we'll sum the error. Okay, now we need to use the solver, but before that let's check the formulation once again, and that is ks is going to be here divided by 1 plus a psi to the power n divided by 1 plus, and we forgot 1 here, 1 plus a to the power, and now it is coming. Okay, yeah, now this model is coming like this, the Gardner model, the gray one, the gray line which you see here. Now we need to optimize these fitting parameters. Okay, so for that we'll need to use the solver. In the solver we will provide that we need to minimize this error, and for that we will need to vary these two values. Fine. And then if you click on the solver, then it says that the value of a comes out to be 25, and n 1.77, and now this model fits very well to the experimental data. Okay, similarly the similar things we can do for Richards. Okay, and similarly we can do for Brooks and Corey. So in the same way, if we do this for Richard and Brooks and Corey, then we'll obtain two more results here that will give you the predicted values of these two predicted values of hydraulic conductivity based on the suction head data which is available here. So these results are shown here. These three models are available here, and for that the optimum parameter values are also indicated in the answer, right? So as we move further to one of the question, that is establishing SWCC of a clay in terms of volumetric water content from measured SWCC, that is measured in terms of gravimetric water content. Okay, so in the clays we usually measure the gravimetric water content. We keep the soil sample in a oven, and we measure the how much change in the weight is happening over the time. Okay, and we keep it in a control chamber where the relative humidity can be controlled and temperature can be controlled. Okay, so for that we'll require the volumetric shrinkage data. So for that we'll see, if we see the expression of volumetric water content, that is going to be volume of the water and total volume of the soil. Okay, and if we calculate the volume of the water in terms of a degree of saturation, that is volume of the water upon volume of the void. So it will be volume of the water will be S into volume of the void divided by total volume. Okay, and the volume of the void divided by total volume can be written as the porosity. Okay, so here if you'll see, if S is equal to 1 at saturation, the volumetric water content is equal to the porosity. Okay, so but what we want to see here, that if we put the value of N as E upon 1 plus E, okay, and that is the basic relationship between the porosity and the void ratio. So that value of the theta will be ES upon 1 plus E, right? And the ES is equal to G into W. So if we put it here, then we obtain a relationship between the theta and W, right? So these two volumetric water content and the gravimetric water contents are related using this term. So to obtain the volumetric water content from gravimetric water content, we will need to have the value of void ratio, and to obtain the value of the void ratio over time, we will need to observe the soil shrinkage curve, that is E, and versus here we can write time. So this is right, that to establishing the soil water characteristic curves in clay in terms of volumetric water content from the SWCC in terms of gravimetric water content, we will require the volumetric shrinkage data. Okay, so the next step is in the multi-step outflow method, which we have read earlier, which is used to determine the hydraulic diffusivity. Provides accurate estimation of hydraulic conductivity and residual water content. So what is the residual water content? That when the matrix suction is very high, we cannot take any further water out from the sample. So at the residual water content, if you will see that even the matrix suction which we are managing here, that is UA minus UW, if it is very high, okay, we have taken all the water out from this sample. Okay, now we are at the residual water content condition. So at that point we are not able to take any further water out from this sample, so the water which we will observe here will be very less. So in that case, we will not see any significant change of water level in the burette, which we are using here to measure how much water is coming out, right? So in that case, this multi-step outflow method will not be efficient in calculating, or will not be able to calculate the value of, you see, the value the value of the hydraulic conductivity or the diffusivity. right? So this we can say is not correct, because at the residual state it is very difficult to account for even when there is a significant change in suction. The amount of water that is decreasing is very small, and it is very difficult to monitor the water which is coming out. So generally when the soil reaches the residual state, the increase in the suction results in a very small amount of water leaving from the soil. The sixth question is that the conductivity model given by the Jackson in 1972 is based on the relationship between hydraulic conductivity and pore side distribution in soil. So if we see the relationship of Jackson, that is K theta I is equal to, which we used to solve that problem. So does it relates? It is based on relationship between hydraulic conductivity and the pore side distribution of the soil. So the pore side distribution of the soil, or we can say the term lambda that is account for the pore side distribution in the soil, that is not accounted here. Okay, so here the K is the function of this theta as well as H. Okay, so in that case we can say that this statement might not be correct. Now we have this Birdie model. It is asked that it can be combined with Friedland and Zink model to obtain the SWCC model, to obtain Friedland and Zink SWCC model to obtain the hydraulic conductivity function. So if you'll see the Birdie model, which says that K capital theta upon Ks is equal to Kr, okay, and that will be relative K capital theta is equal to theta square, and this term. Okay, in this term we need to put the value of capital theta, that is the normalized value of volumetric water content. So from the Friedland and Zink, you will see it's very hard to find out the normalized value of volumetric water content, but from the Venn and Gunjan model you can see we can find out the normalized value, and we can put this value in the bundle model. Okay, so this bundle model is usually combined with Venn and Venn Gunjan model to obtain the hydraulic conductivity function. In multi-step outflow technique, hydraulic conductivity function is established through the estimation of diffusivity coefficient. Okay, so we need to find if this statement is correct. So let's see what happens in multi-step outflow technique. That in multi-step outflow method, we find out we use this Gardner equation, right? So from the experiment we will observe that how much water is coming out, okay, at V infinity or at equilibrium, and at a particular time Vt, right? So here in this term we will find V infinity at a particular time Vt, which is a function of t, right? So if we see this formula, this is a y is equal to mx kind of formula. So we see here, if we plot V infinity of minus Vt upon V infinity in reference to against time, then we will obtain a linear plot, the intersection of which is ln 8 by pi square, right? And 8 by pi square, and the slope of which is d pi square upon 4 h square. Okay, so if you see here, this line is linear, okay, and the value of pi square 4 upon 4 h square is constant, so the value of d will also be constant here, right? So how we calculate the hydraulic conductivity from multi-step outflow technique is that first, from the observation we calculate the change in the height, change in the head, okay. We also calculate the k theta, the change in the change in the volumetric water content, k psi, and k theta also, okay, change in the volumetric water content, okay. Then based on this we obtain this term delta h upon delta theta, because we know that d is equal to k times dh upon d theta. For small increments we can write k dh delta h upon delta theta, okay. So we need to obtain this delta h upon delta theta for every small increment, Okay, and based on this we obtain the value of d. The value of d is the slope of this line. Okay, so this is going to be constant, and the value of k we can obtain using this expression. Okay, so we can write the k is equal to d upon delta h upon delta theta. So in that case we can obtain the value of hydraulic conductivity at different increments, right? So here it is right that hydraulic conductivity function is established through the estimation of diffusivity constant, that is d. So first we find out d, then we find out k. And now we have this question that Brook and Corey model provides a continuous SWCC function. So if we again go back to the slide to see the Brook and Corey model, then we'll observe that the Brook and Corey provides the two functions for gravimetric moisture content. The first one is below the air entry pressure, and the second one is above the or equal to the air entry pressure. Okay, so there are two functions. Therefore, this SWCC is not continuous in Brook and Corey model. It has a break at air entry point. Then there is a question: the diffusivity coefficient estimated in the multi-step technique is constant throughout the applied section range for a given soil. So we have seen here that for a particular increment, okay, for every increment, if we'll see that using this Gardner formula, this value of the d is actually the d pi square upon 4h square, that is the slope of the line, and the pi square upon 4h square is constant, so d is also will be constant because the slope is constant, right? So these are all the things we needed to discuss for the tutorial class of week 5. Now I'll request if anyone of you have any questions, then please let me know, or even if you have it later, you can ask me through mail, or you can ask me in the next class. Thank you.